We continue with the mathematics of artificial intelligence as we look at why ChatGPT is basically a probability machine. In the last video, we had considered the five equations driving modern AI, and we saw different equations like the linear transformation, we saw activation functions, loss function, we saw we saw different equations like that. I think there are two other ones. We ended on the note of the attention equation as proposed by Vaswani when they came up with the idea of transformers. So here we are looking at why ChatGPT is basically a probability machine, right? So the learning objectives here include that you'll be able to explain why ChatGPT is fundamentally a probability model. You understand how text becomes numbers, how you'll be able to describe tokens and tokenization. You'll be able to explain next token prediction, understand probability distributions, explain temperature and randomness, temperature here is in the context of AI, not the normal sense, Then understand why ChatGPT sometimes hallucinates. That is, uh, that's why you're looking for references and it then just cooks up something that does not exist. Then you'll be able to build a miniature language model in Python and connect probability theory to modern AI systems. So this is just an exciting playlist, even for me, because it's been such a learning curve. So let's look at the core idea. We are considering ChatGPT as basically a probability model, a probability machine. The core idea is this. Most people imagine ChatGPT as a giant database that stores answers and retrieves them. That's how we see it, right? This is actually incorrect because ChatGPT does not store answers like an encyclopedia. Instead, it repeatedly asks, given everything I have seen so far, what is the most probable token? So what is the most possible answer I should give in this case? So every word, every phrase, every sentence, every paragraph, and essay emerges from repeating this process over and over again. Like, okay, this person is asking this question. What are the possible things? That's why you can ask one question five times and you get a result that are exactly not, maybe they look alike, but they are not exactly the same because of this whole idea. So in mathematical terms now, ChatGPT attempts to estimate probability of the next token given given previous tokens. I think at this point we should talk about tokens in a very clear sense. Tokens for for dummies. Let me put it that way. Tokens for dummies, right? So tokens are fundamental building blocks that appear in multiple technologies, most commonly representing basic units of text in AI. So tokens are basic units of text, units of values in cryptocurrency. But our focus is on AI, right? So in the world of artificial intelligence, tokens are the basic letters or syllables. So the letters you have that AI systems use to read and write language. AI cannot read words exactly as humans do. So it must break text down into smaller pieces. So the rule of thumb is one token is roughly four characters or about 0.75 of a word. So that's just a token. That means 100 tokens equal about 75 words. So why it matters, AI models have a memory limit. So the maximum amount of tokens they can read or output at once, that's their memory limit. Furthermore, developers and users are usually built per 1,000 tokens of text the AI processes. So that's why AI can be a very expensive adventure, as we've been saying, you know. So let's go ahead and talk about human view versus mathematical view. Human view versus mathematical view. Suppose the input is why is the sky blue? So if you prompt the ChatGPT with why is the sky blue? So a human might imagine that ChatGPT understands the question. ChatGPT doesn't basically understand this question, right? So a human being might imagine that ChatGPT understands the question, searches memory and finds an answer and returns it. Mathematically, the model sees something closer to, instead of understanding that question, what the model is saying is, oh, it is saying Y, it is saying is, it is saying D, sky, blue, and question mark. So it doesn't understand like a human. It sees it like tokens like this, like uh word word groups. So the model then computes probabilities for possible text tokens. So now it now says, okay, the next answer is because you started with a why question, so we should expect something like because maybe because it's 0.2, 0.42, probability that the first token should be like 0.21, 8, 0.15, blue 0.05, right? So one token is selected. So what that split second sometimes when it is thinking, what it's doing is it is ranking all the possible answers it can give, and it will now give you the most probable one. So here now, the most probable word to answer is to start with is like 0.42, right? Or D 0.1, it 0.15, and blue 0.02. So one token is selected, appended to the sequence, and then the process repeats. So if it picks because, then it now checks again what are the possible words that should follow because, and then it goes like that. So that's why it's a probability thing. So let's go ahead and check what is a probability machine. A probability machine predicts uncertainty. Rather than saying the next word will be definitely be X, it says the next word is likely to be X with probability P. So just like you saw here in answering the question, the first word to use in answering you should be like because with probability 42, 0.42, D with probability 0.1, it with probability 0.15, and blue with probability 0.02. So it doesn't know for sure whether it should start with because or D. So rather than saying the next word is definitely would definitely be X, it says the next word is likely to be X with probability P. So an example, um, if you impute this, I drink coffee every, so it's more like the predictive text kind of thing you have on your phone that you have used your phone so much that, but for instance, once I start typing my name on my phone, once I put my first name Emmanuel, it automatically suggests JC Anderson because it has understood how I use it so much that it already knows that after Emmanuel, most likely JSON is going to follow, right? So if I impute, I drink coffee every, then the possible next word might be morning with probability 0.65, day with probability 0.18, evening with probability 0.09, week with probability 0.05, elephant with probability 0.0001, So the most probable one will be 0.65, right? So I drink coffee every day. You can prompt it next time and you get every day. But every morning looks like the most probable answer, and then it just outputs that. So language models learn these probabilities from vast amounts of text because it's more like it has access to all kinds of things that people have talked about, coffee and everything. So it looks at everything and says, okay, the likelihood that morning is the word that will come after it based on all the text that has been trained on will determine the word that it outputs. Now, why language is predictable, right? Language contains patterns, as we know, right? Language contains patterns. So consider the capital of France is, once I say the capital of France is, your mind already goes to, it's that for most people actually know the capital of France to be Paris, right? So most people already continue with Paris without even thinking twice. And the reason is uh, because the pattern appears repeatedly in human communication, and language contains grammar, meaning, context, and statistical regularities. And the fact that the capital of France doesn't change that often, maybe it has hardly ever changed. In fact, I mean, we have countries that change their capitals, but that doesn't happen so often that one cannot really, most people will always know, right? So large language models learn these regularities and use them to predict future tokens. That's how the thing goes. So in essence, ChatGPT doesn't understand what you're asking. It's like it only understands probabilities. So if you're asking a question, it's not like ChatGPT is that intelligent to understand the emotions or whatever you're dealing with. But then they work based on probabilities and predict what you are most likely going to get. That's why sometimes you can get some errors. So now we talk about tokens. I think I already made mention of tokens. I went to check Google for that. The real units, tokens are the real units of language, right? In this case, in the case of AI. So ChatGPT does not operate directly on words, like we said. Instead, it uses tokens. So a token may be a word, it can be part of a word, it can be a punctuation, it can be numbers, or it can be symbols. That's what a token is. They're basically the you can see tokens are the smallest units of of language models, basically. So look at this example. You have unbelievable. Unbelievable to ChatGPT might be read in the back end, of course, you won't see all this. It might be read as on, that's one token. Believe, that's one token. Able is another token. So one word unbelievable is now broken down into three tokens, right? Example, ChatGPT is amazing. So here, chat can be seen as one token. G is one token. PT, another token. Is one token, amazing, another token, an exclamation mark is one token. So the exact splitting depends on the tokenizer used. So there are different tokenizers. So the way a word is split up depends on the tokenizer that is used, that is used in that instance, right? So let's go ahead and see, just like I said the other time, ChatGPT doesn't understand your English or your grammar or anything you're asking it, but it understands tokens, it understands probability and all that. And that's why it's more or less like a probability machine. So turning text into numbers now. Computers do not understand text directly. I've said that a lot. They process numerical values. So suppose you have a vocabulary like cat with ID 0, dog with ID 1, fish with ID 2, and bird with ID 3. The sentence catfish then becomes 02. So ChatGPT doesn't, maybe you are typing catfish, but ChatGPT sees cat as 0 because we have this ID and fish as 2, basically. Now the sentence can be processed mathematically like this based on this now. So catfish 02. So you're asking for catfish, but ChatGPT is seeing 0 and 2 based on the IDs assigned. Then we talk about embeddings. Embeddings is about giving numbers meanings. So you see, you assign numbers to words because ChatGPT doesn't understand the words. And then embeddings now help to give your numbers meaning. Simple IDs are not enough. For instance, you have the IDs cat is 0, dog is 1, and fish is 2. So, and this contain no information about meaning at all, right? So instead, language models learn vectors called embeddings. So apart from the IDs, now you now have to talk about embeddings. So instead, language models learn vectors called embeddings. For instance, cat can then you now have 0.42 minus 0.81, 0.05, and so on. Then dog is 0.40 minus 0.7 and 0.17. Notice that the vectors are similar. So you have similar vectors here. Because cats and dogs are semantically related, so their embeddings become close together in high dimensional space. So embeddings allow mathematical operations to capture meaning. So embeddings help us to capture meaning for mathematical operations assigned to words, you know. Then we have next token prediction. So like we've said already, you query ChatGPT, it's not saying your words, it's seeing the tokens, it's seeing the numbers assigned to those words based on the text, the vast amount of data it has learned from, and then it keeps doing. So it predicts the first word and second word, and it keeps going like that. So next token prediction now. This is the central task of a language model. So next token prediction is the central task of a language model. So it predicts the first task, the next one, and it keeps going. So if you say the sun rises in the, it's probably going to predict east because I mean there's been a lot of writing, a lot of talk about the fact that the sun rises from the east. Formally, then, in the mathematical or probabilistic sense, we have the probability of token at t given token 1, token 2, up to token t minus 1. So what's the probability of the next token? What's the probability of that? What will be the next word? Given that, or what's the probability that the next one is going to be east? Given that the first was D, the second was sun, the third was rises, the fourth was in, and the fifth was D. Based on, so it will now evaluate most of the materials and say that, oh, usually it is said to be east. So the model estimates the probability of every possible next token. So you have a lot of probability work going on in the background. So all the answers you are seeing, a lot of work is going in the background. So example now, you have a token and the probability assigned. So east in this case is 0.9, and that's 91% that the next one is going to be east. That's why you most likely get east. So once in a while it can tell you the sun rises from the west based on maybe some errors. I mean, we are going to say something about hallucination pretty soon. So the east with probability 0.9, and that's the highest. So that's most likely what you get. West with probability 0.04, sky with 0. The sun rises from the sky. So that's with probability 0.02. And cat, the sun rises from the cat. I mean, makes no sense. That's that the probability is pretty small, 0.0001. So the token with the highest probability is usually the best continuation, and then it keeps going like that. Now, building a tiny probability model. Let's build a tiny probability model here and see what exactly a tiny bit of idea of what we are talking about. So the following example learns simple word transitions. Imagine uh, we are using a default dictionary here. So from collections now, we have the library here is collections. So from the library called collections, we import default dict. So you have text here. So the cat sat on the mat. the cat ate fish, the dog ate fish, the dog sat outside. These are your texts now. So see what happens. So for the words now, for if you check out my playlist on Python basics, Python basics, you see the nuances of how Python operates, how you operate on strings like that. So text split, so text dot split helps you to split this text up. So you have words equals text dot split, and then you have your model. The model is you have default dict and lambda. So you have default dict int. So you now say for I in range, the length of the words now minus one, then the length of the words minus one. So you have current words I, next is now current words I plus one, next model then. So the model, so this model now is take the current and the next plus equals one. So you keep incrementing like that. So finally, now say for words, this text that have been split. So it means it has broken down this whole thing into the cat sat on the mat, the cat ate fish, the dog ate fish, and all that. So this line is actually, if I can even try to print that and see, let me see. Do I do that? Okay, maybe I shouldn't. Okay, let me do that. Let me do the print. Yeah, let me just do that. So I just print the word so you can see the output of that. Print words now. Okay, we can print that. Then you have your model default dict, and then for word now, next word in model items. Total is sum of next words and all the values, and then you print afterward for next, blah blah, and do all of that. So if you run this now, this is the first cell I'm running. That's why it's going to take a little bit of time, but it's coming on gradually. Yeah, it's done now. Okay, so you see, this first print I did here now is, we are splitting up this words one after the other. So the cat sat on the mat, the cat ate fish. So you see, the cat sat on the mat. So it breaks up all the words one after the other. And of course, outside is the last word. That's why you also have outside here. So that split, that's what it's doing. So now, the question is, after D, you know, after D, what's the next word? Zero. So it is cat with probability 0.4. It is mat. So you see the cat, the dog, you know. Uh, so the cat one, the mat, the cat, the dog. So it says the cat after the cat comes with probability 0.4, mat 0.2, dog 0.4. Okay? Because the cat appears twice, the dog appears twice. Then after cat, what do you have? So sat probability 0.5, ate with 0.5. After sat, so on 0.5, outside 0.5. After on, D for sure 1.0. After my D, another 1.0. Then after 8, fish 1.0. That's 100%. Then after fish, you have 1.0. After dog. So this is a simple, after dog, you have the dog ate or sat. So you have this with probability 0.5 a piece. So that's a very tiny probability model that you have built there. And that gives you a picture of what is really happening in the background. So these probabilities will now determine how the kind of words you get. So how do you understand the outputs now? For possible output now, so after cat, sat is 0.5, et is 0.5. So you can easily see cat sat or cat et. After dog, et is 0.5, sat is 0.5. So the model has learned probability distributions from the split you have done there. So probability sat given cat is 0.5. Probability that you are going to get et after having got cat the first time is also 0.5 like that. So although extremely primitive, this illustrates the basic idea behind language modeling. So now what we've done here is just it's almost nothing compared to the reality of ChatGPT, but this gives you something into the brain box, into what's really happening in the background, right? So we have probability distributions now. So after each generation step, ChatGPT produces a probability distribution. So example, you have token probability Paris 0.8, Leon 0.1, Nice 0.05, and Mass 0.0001. So the probabilities always sum up to 1. So for every next word that is to be generated, for every next token to be generated, you have a different set of probability altogether, and they all sum up to 1. So this distribution represents the model's beliefs about what should come next, right? So the capital of France is And it just comes with all these things. All this probability distribution. Like, okay, it can be Paris 80%, it can be Lyon 10%, it can be Nice 5%, it can be Mass. That's one over what percentage that? That's one over 10,000, right? So this distribution represents the model's beliefs about what should come next. And then we now see the next thing. Why ChatGPT does not always choose the most likely word. So sometimes it doesn't choose the most likely word, right? Suppose the model predicts good to be zero point 0.5, great is zero point 0.3, excellent to be zero point 0.2, banana is 0.0001. Always selecting the highest probability word would produce repetitive text. So if it is always going to produce the highest one, it will be repetitive. So, and it will be easy to know that, oh, it's always giving you the same thing. That's why ChatGPT gives results in a probabilistic manner. It's not it's stochastic, it's not definite. You don't always get the same results for the same prompt. So instead, models often sample from the distribution. So this introduces variation and creativity. One of the issues that we have with generative AI is the fact that a lot of people complain that it can be quite boring and dull and everything. But ChatGPT tries to solve that problem a little bit by being a bit creative. Instead of always giving you the most likely word, it can switch it up sometimes for the sake of variation and creativity. Now we come to temperature. Temperature, don't think about temperature in terms of heat going up or something like that. In this case, in the case of ChatGPT or generative AI, temperature controls randomness. We just talked about the idea of creativity and variation. So temperature controls randomness. So if you have a low temperature T, which is zero point 0.1, we have high confidence, and then we have predictable outputs and high temperature. That's for low temperature. For high temperature, I think I want to distinguish this. So temperature controls randomness. So let me do this. Okay, can I just do this? This, yeah, and then this. Okay, no, not that yet. High temperature, that is. Yeah, good. So low temperature, say T is zero point 0.1. So that means there's high confidence. So the randomness is very low, and it's you have predictable outputs. But for high temperature, you have a temperature of T.1, T equals 1.5. You have more diversity, more creativity, but it is riskier. So temperature reshapes the probability distribution before sampling occurs. So at each sampling step, the temperature comes to play and then gives the distribution in a particular way so that there can be more creativity or less creativity depending on what exactly you want. So look at temperature example now. Imagine the original probabilities. Cat 0.8, dog 0.15, and fish 0.5. Don't forget they always add up to 1, right? Because this is 0.95 and plus this, that's 1. So low temperature makes the largest probability even larger. So low temperature will make cat guaranteed answer. High temperature will spread probability mass more evenly across candidates. So maybe cat can now be with probability zero point 0.6 and dog becomes a bit higher than this and even fish. So that's to guarantee creativity, to guarantee randomness and all that. So as temperature increases, unlikely words become more likely to be sampled. That's why you can see some crazy things like the sun rises from the sky, something quite unexpected because the temperature is pretty high, and and that's necessary for creativity. So here, imagine import number as NP. So imagine the probability is 0.8, 0.15, 0.05. If the temperature is 2.0, that's a high one, right? So you have a scaled situation where you now have the probabilities raised to power 1 over the temperature. So that's probability raised power half. So, and then scaled now, you have scaled dot sum. So you sum up all of that. So if you print that, you see that, originally you had 0.8, 0.15, 0.05. But now that you have scaled it, because the temperature has been turned up, you now have, so the first word that was appearing with probability of 8%, 0.8, that's 80%. Cat now appears with probability of 0.59, or roughly zero point 0.6, which is lower. Dog is a bit higher than 0.25. It's now 0.26 roughly. And then fish, which was 0.05, is now higher at 0.17 0.15 roughly. So depending on what you want. So what if I make the temperature like say 0.5, the probabilities increase. You can see cat now comes with higher probability of 0.96, then dog comes with 0.03, and fish And the last one, fish even is even lower than 0.05. So that's the idea of temperature. If I make it one, what happens? Okay, yeah, nothing changes. A temperature of one makes everything the way it should be. So let me set it back to 2.0, right? And this is what we got. Yeah, so let's talk about the chain reaction effect. So every generated token influences future predictions. So every word generated now is going to, every token rather generated is going to affect what is going to be coming next. So every generated token influences future predictions. Example, if you have the starting text, the scientists discovered a path can be a new planet, another path can be an error in the experiment, which are possible things a scientist can do, right? So, but a scientist discovered a new, of course, if you say a new, the next thing may not be experiments, maybe it's more likely a planet and all that. So after the first few generated was future probability distribution become completely different, and generation is therefore a sequence of interdependent probabilistic decisions. So what you generate now is going to determine what is generated next because it's all about probability. So in fact, some kind of Bayesian probability right there. So why ChatGPT appears intelligent? Well, the model is not explicitly taught. ChatGPT is not explicitly taught grammar, logic writing, and coding, but it still appears intelligent. Instead, it learns from patterns. It learns patterns from data. So it's all about learning patterns from data. So by repeatedly predicting missing tokens across billions of examples, right, it gradually discovers the syntax, the semantics, the reasoning structures, the problem-solving math patterns. Many sophisticated behaviors emerge from next token prediction alone. So the fact that, it's learning from data. So next token prediction can then become a bit more creative and all of that. So that's why ChatGPT appears more intelligent. Now, I used ChatGPT in the very early days, let's say late 2002, early 2003. I remember I did some math thing then, and they were totally wrong. So I had to even say, oh, the answer is not this, it is that. But over time, it has got a lot better. That I can even do some crazy, some mathematics on her, like that had been even defying human attempts. So why hallucinations occur, right? Hallucination is, ChatGPT giving you wrong answers sometimes, right? So ChatGPT predicts likely text. It does not directly verify truth. Suppose someone asks, who won the Nobel Prize in Physics in 2070? I mean, no answer exists because we are not even in 2070 yet. However, the model still attempts to continue the text. The result may be a plausible but invented answer. This phenomenon is called hallucination. In fact, let me try this with, not with ChatGPT, let me try it with Grok and see what happens. Who won the Nobel Prize in Physics? Let me just copy and paste to save time. Okay, I copy this now. Then let me go to another model, Grok. All right, so I just come here, throw this in. Who won the okay, good. This one is wise enough to tell me no one has won the Nobel Prize in Physics in 2070 yet. The Nobel Prize are awarded annually, usually in October for achievement from the. Okay, so this one tells me. So I think ChatGPT 2 should be is good, should be able to tell me that reality, you know. So so we have a new chat. I have this. So who won the Nobel Prize? Okay, yeah, good. ChatGPT is able to catch that. So no one knows yet. As of June 2026, the Nobel Prize have only been awarded through 2025 and the winners. So now at the early stages, it would have maybe cooked up some answer. It would have given you a name that that doesn't which wouldn't be true, right? That's hallucination. So no answer exists. However, the model may still attempt to continue the text. So the result may be a plausible but invented answer. This phenomenon is called hallucination. So when sometimes you get maybe you find 5 combination 3, which is supposed to be 5 factorial over 3 factorial 2 factorial, and then that's a 5 factorial 5 times 4 times 3 factorial 3 cancels that, which is supposed to be 10, and you get maybe 20, so that's hallucination right there. But the better the models get, the better the accuracy will be, and the accuracy has been, right, basically from my experience. So training a language model now. So training involves predicting missing tokens repeatedly. So training is all about predicting missing tokens repeatedly with some accuracy. So example, if you input the moon revolves around the dash, okay, the target is the Earth, right? But if the prediction is wrong, the model adjusts its parameters. So this process occurs trillions of times during training. So if the predict once the prediction is wrong, and that's why sometimes you're even allowed to. I think in ChatGPT, you can be asked if the answer If you like the answer, you don't like it. So if you give some thumbs down, that is also you contributing to the to future predictions. So because you have given thumb down or thumbs up, that's going to decide how the future predictions will look like. So if the prediction is wrong, the model adjusts its parameters. This process occurs trillions of times during training. For example, in data set, right, you have a prediction which is model example dot input, error loss, error is equal to loss in prediction and example target, and then you update the parameter. So this is just a good example in a particular data set. So let's now talk about the mathematics behind language modeling. So the model attempts to estimate the probability of an entire sequence. So that's what it's about. So it's to estimate the probability of an entire sequence. So you have probability word one, word two, word three, up to word n using the chain rule. So you have probability that using the chain rule, then you have probability word 1, word 2 up to word n, which is equal to probability of word 1 times probability word 2 given word 1, probability word 3 given word 1 up to word 2, and all the way down to probability of the nth word given the first, second, up to n minus 1 first word. So this decomposition allows the language model to generate text one token at a time. So the decomposition allows the language model to generate text one token at a time. So so let's look at a slightly more realistic example. Following the following model samples from learned probabilities, right? Imagine you import random because we want some element of randomness. So if I say I, so after I, love, so love should come with probability zero point 0.6, like should come with probability zero point 0.4. Then after love now, so Python probability zero point 0.7, AI Python probability zero point 0.3. Then after like Python should come with probability zero point 0.5 and coffee with probability zero point 0.5. So then if the current word is I, so then the sentence now, if you now do this current sentence, so sentence now is current, that is in some initialization, right? So you pick the current. So you now go for I in range 2 in the range. So that's 0 and 1. So choice is you list the transitions, the currents, and dot keys, then probabilities, list transitions. So based on all this now, so the currents you have the random choices from choices and probabilities for the first one, and then you append the current and print. So and you join the sentence up together. So if you run this now, you now see I like. So if it goes for I like, so that would most likely be well, it could also be coffee, but it's random, right? So it can keep changing. So this one is saying I like coffee, so it's stuck with I like coffee. So it's still I like coffee all the way. So I keep going. So now it says I love Python. Okay. I love AI. I love Python. I love Python. I love Python. I love AI. I like coffee. I like coffee. I like coffee. I like Python. I love Python. I love Python and all that. So that's the kind of thing there. So that's a slightly more realistic example. Now let's talk about n-grams versus transformers. So um n-grams versus transformers. Older language models used n-grams. Example, probability that the word at t, given word at t minus 1, word at t minus 2, only a few previous words could be considered. So because you couldn't go all the way to all the words. So modern transformer models can attend to thousands of previous tokens. So it can generate the 1000th word based on the initial 1999 words that had been predicted. So this enables long conversations, code generation, reasoning, summarization, translation. The underlying goal remains next token prediction, but the context window becomes dramatically larger. So these days with transformers, things are way better instead of in the time of n-grams where only few words could be accommodated for to predict the next token. So let's look at a big misconception about it. Many people hear ChatGPT predicts the next word and conclude, therefore it cannot reason. Of course, it's still, though technically it can't reason, right? But because of the mathematical basis, this is misleading. So a chess engine chooses one move at a time, right? Yet sophisticated strategies can emerge from that. So similarly, repeated probabilistic predictions can produce out of probability, sheer probability, without even understanding grammar. It can produce planning, reasoning, explanations, mathematical solutions, computer programs. Complex behavior can emerge from simple local decisions. So if you check the first video, you discover that the whole building block the mathematics building block for building block for AI. Very simple concepts like something like the line of the equation of a straight line, which the linear idea of linear transformation is about. So our key takeaway so far is as follows. ChatGPT is fundamentally a probability machine because text is converted into tokens, tokens are converted into numerical vectors, neural networks estimate probabilities for possible next tokens, a probability distribution is generated, one token is selected, the process repeats until the response is complete. And then the central objective is this that probability that of the next token given previous tokens. Basically, that's the idea. What's the probability of the next word to be generated given the previous words? So everything else then emerges from performing this task at a normal scale. So AI is all about doing simple tasks tons of times and then it becomes something really out of this world, so to speak. So we have the final mental model. Imagine a superhuman, imagine a super Imagine a superhuman autocomplete system that has read a substantial portion of human text. At every step it takes, given everything written so far, what token is most likely to come next? By repeating that process hundreds of times for each response and learning from billions of examples during training, modern language models generate coherent conversations, essays, code, explanations, and reasoning. That is why ChatGPT is fundamentally a probability machine. So probability is running this whole thing, right? So yeah, we have some questions to chew on. So I'll display. Of course, I'm going to solve two of them as usual. Let's see. The two I'll be solving are problems 18 and 20. So explain why ChatGPT is better described as a probability model than a database of facts. So why that's in essence explaining why ChatGPT is not Wikipedia, right? So you have all that. The vocabulary contains 75 tokens. Explain why ChatGPT must assign a probability to every token in the vocabulary during generation. Of course, we saw all of that. You want to, with what I've said so far, I should be able to answer that now. So we can see 1 to 4 clearly here. 1 to 4. Then now we have 5 to 7 clearly. 8, we can go for 8 to 14. I mean, for now, 8 to 14. Then 15, 15 to 18. We can see all of everything from 15 to 18. And lastly, we can see 19 and 20. And like I said, I'm dealing with 18 and 20. So 18 is about, suppose the model has learned probability that B given A is 0.6, probability that C given AB is 0.4, probability of D given ABC is 0.5. If probability of A is 0.2, compute probability A, B, C, D. Then the next one is imagine that future language models become 100 times larger and are trained on vastly more data. Based on the probability machine framework, explain how their probability estimates might improve and how that could affect generated responses. So I'll be answering these two questions as we bring this to a close gradually. So um, let's go for that. Oh, this from the previous video, but it's okay. So let's go for this now. Problem, talking about problem. Oh, okay. I have to change this. Problem 18. Problem 18. So suppose a model has learned, suppose a model has learned probability B given A is 0.6, then probability C given AB is 0.4, and probability D given A, probability D given A, B, C is equal to 0.5. Now, if probability of A is 0.2, then we are required to compute probability A that the words generated will be A, B, C, and D, like that. Okay, that's the question here. So I move on with that. So step one, right? Step one, we apply chain rule. So for the solution, step one, we apply chain rule for 4 events. That's A, B, C, D. For 4 events, the chain, the chain rule gives the chain rule gives probability A, B, C, D, which is probability of A multiplied by probability B given A multiplied by probability of C given A and probability of C given probability of C given A, B, A, B, yeah, A, B, right? Probability of C given A, B, and lastly, probability of D given probability of D given A, B, and C, like that. Then we substitute the given values. That is 0 0.2 times 0 0.6 times 0 0.4 times 0 0.5. So all of that, so all of that together will have to be 0 0.024. Okay, that's what we get there. So what that means is that thus, thus the probability, the probability of the complete probability of the complete sequence occurring is 0 0.024 or 2.4%, like that. So that's problem 18. That's problem 18 taken care of. So we move on to the next one, problem 20. So that's more of story. Problem 20 says, imagine that future language, imagine that future language models become 100 times larger and are trained on vastly more data based on the probability machine framework. Explain how their probability estimates might improve and how that could affect generated responses. Okay, this is some reasoning kind of thing. So we go for the solution. Step one, right? In step one, we have to recall the core task. Recall the core task. So the fundamental objective, the fundamental objective of a language model, is to estimate probability of next token of the next token given previous probability next token given previous tokens, like that. So the better this probability estimates become, the better, the better the generated text, the better the generated text becomes. Okay. So, and then we go for step two. Step two. In step two now, we look at the effect of more parameters. Effects of more parameters. Okay. So now the language models are becoming 100 times larger, right? So we say that a larger model, a larger model can learn more complex patterns, more complex patterns. For example, for example, it may better recognize long range dependencies, long range dependencies, dependencies. Two, rare linguistic structures, rare linguistic structures. Then technical vocabulary. Then subtle contextual cues, subtle contextual cues. So as a result, probability estimates, probability estimates become more accurate. Probability estimates become more accurate. Like that. Then in step three, we talk about effects of more training data. Effects of more training data. Of course, more data means more, more, more clarity, right? More data exposes the model to more facts. So more data means more facts, more writing styles, more writing styles. Okay. More writing styles, even more languages, right? More languages. Then more examples of reasoning, more examples of reasoning. Okay. Now, this allows the model to estimate, this allows the model to estimate probabilities using a richer statistical foundation, a richer statistical foundation. Then we talk about impact on generation. Step four now, impact on generation. So impact on generation. So more, more accurate, more accurate probability estimates, more accurate probability estimates generally produce, generally produce more coherent responses, more coherent responses, fewer contradictions, fewer contradictions, better reasoning, better reasoning, better code generation, better code generation, better contextual understanding, better contextual understanding. Then fewer hallucinations, fewer hallucinations. Okay. For example, for example, for example, instead, for example, instead of assigning token probability, instead of doing this, instead of assigning token probability to be, say, correct answer 0.45, wrong answer 0.35, and then the other answer 0.20. Instead of doing that, a stronger model, a stronger model can say, so let me do the stronger model now. The stronger model can then have another, because of more data and everything, the stronger model can then have correct answer to be 0.85, which is way better than 0.45. And then the wrong answer is 0.10, which is way lower than the wrong answer, which is desirable, right? And then the other answer is just 0.05. It makes things way better because we have more data. So this definitely be a stronger model. So, and that way, it then therefore correct, making correct making correct generations much more likely. So in conclusion, then, so in conclusion, within within the probability machine framework, within the probability machine framework, larger models, larger models, and larger data sets, and larger data sets improve the estimation, improves the estimation of the simple thing probability, next token, given the context, and improved probability, and improved probability, improved probability estimates typically, typically lead to more accurate, leads to more accurate, coherent, coherent, reliable, and useful responses. Okay, so with that, we come to the end of this interesting video again. Um, Once more, like I always do, I'll flash the questions, and then that'll be all for this video. So practice problems. You have questions 1 to 4. Okay, maybe we can have up to, okay, if I cover this, we can see 5. Okay, we can see. So 1 to 4, clearly everything 1 to 4. Then 5 to 7, clearly it's in there. 5 to 7. Then 8 to 14. Okay, 8 to 14. 8 to 14 like this. Then 15. I can see all of 15 to 18. 15 to 18. Then finally 19 and 20. 19 and 20. So with this, we come to the end of this interesting video about why ChatGPT is basically a probability machine. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges that you'll find as you click. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.